Let's start with a thought experiment. Picture a ring of uniform positive charge. Now, imagine taking a tiny positively charged test particle and placing it exactly in the dead center of that ring. Because the test charge is positive, the ring repels it. Since the ring surrounds the charge evenly, those repulsive forces push inward from all sides at the exact same strength, leaving the particle stationary. Due to this perfect geometric symmetry, the net electric field at the direct center of the ring must be exactly zero. But we need to see what happens when we leave the center. Let's move our hypothetical test charge out along the central x-axis to an arbitrary observation point, P. This diagram illustrates the shift. The off-axis forces cancel out, leaving a single net force vector pointing away from the ring. The red boxed formula defines this exact field strength E, determined by charge Q, radius r, and distance x. This single foundational expression allows us to calculate and predict the electric field's behavior at any coordinate along the central axis. We can test this equation against our earlier intuition. Look at the bottom left. If we plug 0 in for x, returning us to the ring's center, the numerator becomes 0, proving mathematically that the electric field is 0. Now we'll look at the opposite physical extreme. Imagine observing the ring from a massive distance, where the distance x is far greater than the ring's radius r. The approximation text on the right shows how the algebra simplifies. Because x squared is so dominant, the r squared term disappears from the denominator. After canceling out the x variables, we are left with the reduced equation shown in the bottom right box. This tells us that from a great distance, the physical size of the ring no longer influences the field. The entire system behaves like a simple point charge. This graph plots our findings so far. Since the field is 0 at the center and eventually returns to 0 at infinity, there is an unexplained transition happening in the space between. For the field to rise from 0 and then fall back to 0, it must reach a point of absolute maximum strength somewhere along that path. To find that specific coordinate, you can pause the video here. Apply the quotient rule to take the derivative of our field equation with respect to x, then set that derivative to 0. Solving for x reveals that the field reaches its maximum specifically at a distance of r over the square root of 2. The white box at the top left shows the final equation for the maximum electric field, which we find by substituting that specific x value back into our master formula. Through differential calculus, we move from observing general trends to identifying the precise boundaries of physical forces. On the right, we fill in the missing curve. The field rises to peak at E max, then descends toward 0. We consider the negative x-axis, left of the center. Moving left points the force vector negatively, creating this mirrored dip that reaches negative E max. This complete graph provides a total map of both the magnitude and the direction of the electric field at every point along the central axis. Let's strip away the derivations and focus on the practical foundations. We analyzed a physical ring of charge by tracking 3 critical states: the zero field center, the distant point charge approximation, and the balance point where the field reaches its peak. This summary combines our master formula, the distant point approximation, and the completed plot mapping the field's behavior. Understanding the electric field of a simple ring provides the analytical framework needed to deconstruct much more complex charge distributions in physics.